for the basis elements, and then you're done.
Yes, that's what I've been doing.
Yeah.
It seems to make a lot of sense.
Yeah, it feels right?
Yes, or like, I know for, I think it's case 3, it's a union of basis.
Correct.
But
Well, yeah, you have to, that is not, it wasn't obvious to me why minus infinity to 0 as an open interval would be open in the half, the lower limit topology. So you have to prove that.
Okay, I said.
And stick charm. And I said that.
I stole it.
Oh. Was that like a test? Like
No, I do things like that. I think I kept Skylar's water bottle for over a year in the office. I didn't use it. I just had it in the office.
That's
Skylar's an interesting capstone student because he's very similar to me. So we're just a mess. We're just a mess. He went to obesity week with me last year. My phone was in, it's a conference. It was in San Diego. I did not have, my cell phone was dying like all the time. As soon as I unplugged, it would die. So something was wrong with it. Skylar always forgot to charge his. And one evening he decided he's going to take me back to my hotel. We had the government issued hotels far away from the conference place. Both of our phones were dead. We have no directions. Like, didn't you have to take land nav? Don't you have any sense of direction? He's like, no, ma'am, I didn't do very well at that. Like, yeah, we're in trouble. Like, there's no way to get to the hotel without knowing where it is.
No, I mean,
I know. All right, so I'm just gonna write down, the proof is pretty straightforward. It really has to do with unions and functions, but the big theorem that Tim has been using liberally.
liberal. I speak liberal. We should get it. Liberal, sorry. Oh, sorry, that was an internet joke that meant spoken about.
That's a good one.
It's a good one. Tony Napolitano speaks on to straight lead right now. That was like his joke.
I would type you as chronically on.
What?
I would you as chronically on.
Just because.
This is the layperson theorem version of the theorem, which I think not just him, everybody's been using it, that you're just taking basis elements and then inverting them to see if the basis elements are open. So there's something natural about just using the basis elements. But as you look over at Sebastian's board, or I just wrote, not all open sets have to be a basis element. Minus infinity to 0 open is a union of basis elements. And you can get some pretty bizarre things like the complement of the Cantor set as being open. So if you just did it for any arbitrary open set, it would be a nightmare if you had to show that. So the formal statement is, if I have X and Y are topological spaces, and B is a basis for Y, then F going from X to Y is continuous if and only if F inverse of B is open in X for all B belonging to B. And the proof is pretty straightforward. I'm not going to do the proof of this one. So on your boards, if you look at them, that's exactly, you were using this theorem. You weren't actually taking every arbitrary open set and showing that it inverse is open. That tired, Nicole?
Talk to us next year when you guys.
You don't have to worry about that.
Just give me my bachelor's degree.
I'm just going for NSF and nothing else. I'm good.
That might be actually smart to try one and put all your eggs in that basket, actually.
I mean, I don't.
That sounds sarcastic.
No, I actually think that's how, that's exactly how I apply for grants. I do one and I do it really carefully and spend a year on it. And I've got a pretty good funding rate.
Mhm.
And you send 4 of them out, you're not gonna pay attention to any of those 4. So,
It's like two of them. Yeah, because my career path now, what I wanted to is, you know, if I don't find compliance, come back here and teach. And then go back out and come back here and teach again. So it's like, they'll send me to graduate school anyways. It's just as to whether or not I want to avoid the ad zone. Like if I get NSF, then I can just defer it until I come back here.
there's also a program called AI2C. I don't know if you guys have heard about it. They started picking up people a few years ago, like, I think 2018 was when I saw the first cadets that came out of here, right, asking for letters of rec to go into this program. And they're trained at Carnegie Mellon. Then they work 3 years at the site in Pittsburgh. So they're really working with Carnegie Mellon professors for 3 years after they get their masters. And Bryce Wilkins is the first to go through that program, and he's asked to teach here. So he literally he did Lincoln Labs. So he went from Lincoln Labs to AI2C's Carnegie Mellon. And I think he also went to Columbia, but then he did his 3 years at AI2C and now he's requesting to come back here.
Yeah.
So he hasn't been in the army yet.
Yeah, he's an air defender.
Yeah, he just air defense.
What's that?
Everybody in that program, the ones that I met were West Point grads. Everybody was branched different things. They weren't cyber or MI. They actually were branched different things. And that was before data science was here. Okay, this is an analysis lover's theorem, and I'm, by the way, an analysis lover, I'd admit it. My training was all in analysis, functional. So all that stuff that with measure theory, that's all linked. It's the mathematics of PDEs, the mathematical side of PDEs. And so we just love sequences. The analysis is about limits. So this is theorem 4.7, but you can tag it as the analysis lover's theorem. Assume, I love this theorem. F is continuous with xn converging to x, with the definition convergence being the topological definition. Then the limit as n goes to infinity, f of xn is equal to f of, this is the way I'm writing it. He didn't write it this way. So this is an important theorem for partial differential equations because often you are constructing a solution to a PDE, but you don't know what that solution is. You want to show that this solution actually exists. It gets pretty complicated. So what you'll have is you'll have a sequence of maybe functions of compact support that do certain things that are nicely behaved. And you can show that in the limit, it actually converges to what it's supposed to converge to. And that's how you bootstrap up the solution to a PDE. Just because you write down a PDE doesn't mean it has a solution. And so you need this theorem throughout. And that's why we pick these nice functions that have compact support. They're continuous with compact support. Well, we didn't define compact support, but we'll get into that. So basically, this tells you when you can pull a limit inside and outside a function. You also have this in integrals a lot. You'll have sequences of functions that are inside an integral. You'll want to know, can I pull the limit outside the integral? Now, the integral itself is a limit, so you have a double limit to worry about. So these kind of theorems are the kind of things that you work in analysis.
Doctor, for the part about with x and sub n going to x. Is that like a condition that's in the thing?
Yes, you have to have that convergence. So think of the function that you have on the board. in the usual topology, I could make the sequence be xn equals 1 over n, and this is not true in the usual topology. Right? Because that function is not continuous in the usual topology. So the limit inside is going to give you f at 0, which is 1, but the limit outside is going to give you, so I should have taken minus 1 over n. So minus 1 over n goes to 0. So the limit inside is f at 0, which is 1. But if you pull the limit on the outside, you're going to get 0. So I'm doing a lot of hand waving. Where's this chalk I stole? So if you have, this is not true. In the usual topology. That's true. You just look on the board. Tim's really nicely written it down for every minus 1 over n. That's going to be, and then the negative side. So f of minus 1 over n is 0. But if I take the limit, these don't equal. So the limit on the outside doesn't equal the limit being pulled on the inside. No, there's no such thing around a topology, right? I could make a continuous function on those finite sets. The weird example. So this is just an example, a concrete example showing you that I need continuity. But you don't have to even have intervals, right? You can have something bizarre. So if f is continuous and you have a convergent sequence, by definition of convergence topologically, then you can do this. You can pull it.
So f can't be continuous if it's only defined over a certain interval in a topology. So like if I only define f from -5 to 5.
F usually, when we define f going from x to y, all of x is covered inside f. So it doesn't make sense. But I think you're going to this compact support thing. So you can come up with functions that you want it to kind of be 0 everywhere else, and only at like a particular spot you want it to do something. So they use this in physics a lot, where they'll have sequences of functions where they're something and then 0 everywhere else. But compact support means that you use it in 476. 476, you use that. They have these distributions defined by a PDF with a function that has something defined on an interval, and then everywhere else is 0. All right, this is used a ton in physics and engineering. If an engineer makes a mistake, it's usually because they didn't check that f was continuous. And they find us really annoying, but you didn't show that your function's continuous before you did that. They had a problem here actually at West Point where they were taking images and half-toning them, and they were using arctans, a sequence of functions of arctans, to actually be the Heaviside function in the limit, because neural networks use -1, discontinuous things. And when they half-tone pictures, made black and white cells for everything, which is -1 and 0, or 0 and 1, what would happen is in the limit, they would get this flickering occurring at 0. And so they came to me and asked me about that. And I said, your function, the limit's not continuous. The function, the actual application of what you're doing, these sequence and functions, you can't pass to the limit because it's discontinuous. Question, Michael? Yes.
Here.
I think I'm going to write it down again. Yeah, I'm going to write it down again. Just to remind you. With neighborhoods, remember we did it and then we went back and looked at the analysis definition of convergence. So maybe it's good that I'm as busy as you guys, because I rewrote the definitions for myself and I thought, okay, if I forgot these, then these guys probably forgot it. So this is used a lot in physics and engineering. So I am going to prove it. So we must use, see, I knew what you were going to ask me. the definition of convergence. So recall, see, I was ready for you. In a topological space, X, a sequence of functions or a sequence of points, Xi, which is a subset of the X, converges to little x belonging to capital X if for every neighborhood U of X, there exists a capital N belonging to the natural numbers such that Xn belongs to U for all n bigger equal n. Ringing a bell? And I even had you guys look back at the standard analysis definition with absolute values and change them to be balls. I just gave those back to you, those in-class assignments. Sebastian?
Yes,
Yeah, we did do it. We did some stuff in here, but was it before I left for, I think it was before I left for Maryland. I think at the day I kind of told you, like, it's incredible. You can define things like convergence and continuity without having any notion of distance, only with sets. All right, so to prove this, here's my no. I know F is continuous. And I'm just going to label that out the way you do in foundations. And I also know that Xi converges in X. So you want it. So those are the two things I know. I want to show this makes a sequence in the Y space. That's what we want to show. This is almost like a foundations proof, where you just write down what you know, write down what you have to show, and it kind of spills out. They're complaining about MA 103. Okay, so got that labeled down. Hang on, I'm gonna change colors. This one? Okay. So I'm going to start with a neighborhood. If I'm going to show convergence in the Y space, I've got to get a neighborhood. I've got to use that definition of convergence. I've got to get a neighborhood. I've got to get a capital N. I've got to get the sequence members are all in that neighborhood. So that's what I have to do. And I don't have any capital N's yet, but I know Xi converges, so there's a capital N there. So I'm going to try to pull what I know from the X space into the Y space. That's the game plan. So if I start with a neighborhood of f of X, in Y. Since F is continuous, I have to now go some back to the X space because all my no is in the X space. So since F is continuous, we know F inverse of U is open in X. We also know since the xn's converge to X. I'll do that on the next slide.
So that's by the theorem, the first.
Which is it's from continuity, right? So just because F is continuous, like what you just did on the boards. Or I say any neighborhood can open that in the Y space. We know F inverse of that open interval open set has to be open in X. So I'm just using the definition of continuity right now. We also know that since F of X belongs to U, X must belong to F inverse of U. That's because the definition of F inverse of U is the set of Z belong. That's what you do in foundations, these kind of set things. I know that's what you do in foundations because that's what we're doing in foundations right now. So I'm going to call this star so I don't have to rewrite it. So I know those two things. So by definition of xn converging, I know there exists an n, blah, blah, blah. Rewrite the definition. Such that xn must belong to this open set is a substitution, right? I just replaced the open neighborhood with this inverse image. And that's got to be true for all n bigger or equal n. So I'm just copying and pasting from my no, which I think I labeled as 1. No, 2. And I think in the definition I gave you, so I'm using use, but in the definition I gave you, this is an open set. And in the definition I called that U of convergence. So xn belongs to an open neighborhood. So therefore, I know this definition of convergence means that there is a capital N. So now I've got my capital N. That's it. Done. That's the definition of convergence in the Y space. I think I'm going to end with 2 boring things. I'm going to give you 2 factoid theorems. But the next class we have is going to be really fun. We're going to go to the punctured sphere and do some stuff in 3-dimensional topology. I really want to get all the way to knots. He actually introduces knots at the end of the section on continuity and homeomorphisms. But I was already, I think, at like 18 pages of notes, 15 pages of notes like that. Okay, wait, I'm going to back off a little bit. It's going to get really cool. Huh? Squishing shapes. Come in there. We're going to squish shapes. Okay, two factoid theorems. I call them factoid theorems because they're just like the ones that you guys had for open and closed, like to show the closure does this. You had like this laundry list of facts and then you use them. So I call them factoid theorems because they're used to prove other theorems. One is that inverses of closed sets are closed if and only if F is continuous. That's the layperson version. The adult version is if I have X and Y be topological spaces, F is continuous with F going from X to Y, if and only if F inverse of C is closed for every C contained in Y closed. This just has to do with whether you can pull complements inside or outside functions, which, yeah, I don't use a book for foundations. So we kind of hop through different topics. So I make up my own problems. And I gave them the problem of asking them if I have a function, can I pull that complement outside of the thing? I didn't know if it was true or not, just gave it through to them. It was a great problem, wonderful problem. So that's actually not true all the time, but and the second fact is the composition of continuous functions is continuous. Compositions are operations on functions. And if you took abstract algebra, you probably saw that there if they had examples that work on function spaces. So if you think of, it's not calculus that we're really after, we're actually wanting to do calculus on top of functions. That's the analyst side of me. So when you look at a function on top of functions, like try to think of a good example. So if you look at square matrices and they have the property that they're symmetric, A transpose A is equal to A transpose. On that set, you actually have a one-to-one mapping with those matrices and the complex plane using eigenvalues. And then you can actually do calculus on top of the matrices. So the matrices are themselves are functions, but you consider a matrix as a point. And then on top of that, you can do calculus. You can talk about what it means to take the derivative of a matrix function, which is pretty amazing. So we're composing functions all the time. That's the operation that we used. If you want algebraic structure. So all of that it just comes together as one for looking with composition. So composition is super, super important. And that you have closure for continuity under composition is a big deal. All right, let me give you the formal definition of this and then we'll close. The adult version is let F go from X to Y and G go from Y to Z. F and G are continuous on X, Y, Z topological spaces. Then G composed with F going from X to Z is continuous. The reason all of this stuff is important is usually you sometimes want to prove something over in some space and it's hard to prove something there. And you have this other space that is easy to prove in here. And you have this intermediate space where you can actually go from one to the other with a map easily. And you know that you can go from the middle space to the end space with a map easily. If you can compose those functions, then you can go from the planet where everything's easy to prove to the planet where everything's hard to prove by skipping over this middle one in the center. So that's why we use this theorem a lot. Lauren?
The G circle F, that's G of F.
It's G of F of X.
Okay.
So you make a new function out of old functions. That's why we call operating on functions, because when you matrix multiply, actually we were just laughing about that, but when you matrix multiply, you're composing functions. That's really what you're doing. I think they should teach it the other way around linear algebra. They should do linear functions as functions first, and then show them, hey, these are really matrices. Because that's the point. This is why they don't let me make decisions here.